Hi, this is Mrs. Kidman, and in this video, we are going to be discussing the fundamental theorem of algebra. So in previous videos, we've talked about how we can solve polynomials, and we've talked about how we can do it by factoring, using the rational root theorem, we can do it by graphing, but how do we know when we found all of the possible solutions? That's really a question that we run into. We find some solutions and we're like, is this it? But how do I know if that's all the solutions? Well, we have something called the fundamental theorem of algebra, and that theorem basically talks about a couple of different things, but overarching, what it talks about in a corollary of it is that the number of possible solutions is the same as the degree of the polynomial, both real and imaginary solutions. So what that means is by the time we finish finding our solutions, we should have the same number as the degree. So with that being said, I want to take a look at this problem here. Let's consider this graph. Okay, so we have the one x cubed minus 3x squared plus x plus 5. So as we take a look at this graph here, we know that the fundamental theorem of algebra tells us that because this is degree 3, I should have 3 solutions, or 3 zeros. But when I graph this, notice how there's only one place where it crosses that x-axis. Now the places where it crosses the x-axis are going to be our real solutions, which means that because this has 3 solutions, but only one of them crosses the x-axis, that implies that the other 2 have to be imaginary solutions or imaginary roots. And this is so important to be aware of, because as we're trying to find those solutions, if we graph it and we see that there's only 3 numbers there, but it's a 4th power polynomial, a 4th degree polynomial, we know that there has to be more solutions out there. Now, the beautiful thing about imaginary numbers is they come in what we call conjugate pairs, which means that for every one imaginary number, it comes with a partner. So we will never have imaginary solutions in odd numbers. We're always going to have 2 imaginary solutions, 4, 6, 0, things like that, but they're always going to come in a pair, come together or not come at all. We're never going to see just one imaginary solution. So that's something that is super cool about them. So we always know that there's going to be at least an even number of them. So let's take a look at a couple of examples of how we can use this fundamental theorem of algebra to help us find all of the solutions. So let's take a look at this first polynomial here. Now this polynomial is actually the same polynomial that we saw on the previous page. So with this degree of 3, that means that I'm going to have 3 solutions. But as we saw on the graph on the previous page, there's only going to be one real solution. So we've got 3 solutions, but only one real one. So let's take a look at what that one real one will be. Well, if I try to factor this by grouping, it's not going to work out pretty. So instead, I'm going to use that rational root theorem. And I know that x has the options of being plus or minus 1 or plus or minus 5, because the only factors of 5 are 1, 5, -1, and -5. And our leading coefficient is a 1. So then what I want to do is look at that graph to decide what is that value that I think it's going to be. In this case, I see a -1. So I'm going to test with synthetic division to see if that -1 is actually a factor. So as we run through this synthetic division here, we end up getting a remainder of 0. So what that tells us is that this polynomial actually factors into f of x equals, remember it's going to be the opposite here, so x plus 1 times x squared minus 4x plus 5. Now, I don't know about you, but I can't come up with a number that multiplies to 5 and adds to -4, right? That just doesn't work. So instead of trying to factor it using this x method, what I'm going to do is I'm actually going to factor this out one more time using the quadratic formula. So let's go ahead and do that. Remember, our quadratic formula is x equals -b plus or minus square root b squared minus 4ac divided by 2a. So let's go ahead and plug these in. We get a 4 plus or minus the square root of -4 squared minus 4 times 1 times 5 all over 2 times 1. Okay. And so then we end up getting 4 plus or minus the square root of 16 minus 20 over 2. 4 plus or minus the square root of -4 over 2. Okay, pause here. So the square root of a negative, if we do that in our calculator, we're going to get an error. Because remember that the square root of -1 is the same as I. That's how I is defined. So really what we have here is not 4 plus or minus the square root of -4, but we actually have 4 plus or minus 2i over 2, which simplifies to 2 plus or minus I. So then that tells us our three solutions, because what are they? We have our one real solution, which is a -1, which we found right here using synthetic division. And then based on what we got after synthetic division, we can use that quadratic formula to then show that our other solutions are 2 plus I and 2 minus I. So in this case, our three solutions, just like we saw before, have one real root and two imaginary ones. So let's take a look at a couple more examples where we decide how many solutions should I have, and start by finding those real solutions. If we find all the real solutions that we can, then we'll look at imaginary solutions. So let's take a look at this one. How many solutions are there? Well, the degree on this one is a 1, so there's going to be one solution. So let's find it. Remember, we want to set this polynomial equal to 0 and solve for x. So then we get 1 equals 2x, and x equals 1/2. So that is our one solution. In this case, we have one real solution. Okay, what about this one? Because it's a degree 2, we know we're going to have two solutions. And so as we set this equal to 0, what I'm going to do is I'm actually going to subtract 2 from both sides, and we get -2 equals x squared. And remember, the opposite of x squared, to get rid of that squared, is to square root. So we get that x equals the square root of -2, which is really plus or minus I root 2. So our two solutions here are going to be x equals I root 2 and negative I root 2, where I is that square root of a negative. And so in this case, we actually had two imaginary solutions. Okay, let's take a look at one last problem here. So find the number of solutions in this. So I'm going to try factoring this one by grouping. So we've got x squared times x plus 1, -1 times x plus 1. Then we get x plus 1 times x squared minus 1. Now, we need to know where we can stop. How many solutions are there? Well, in this case, there are 3 solutions. How do we know? Because it goes to that power, it has that degree of 3. And then we found one piece here. We need to then factor this to find that other solution. And this is actually a difference of squares. So we've got x plus 1, x plus 1, x minus 1. So what are the 3 solutions there? Well, if we set each of these equal to 0, we get x plus 1 equals 0, which means x is -1. X plus 1 equals 0, which means x is -1. And x minus 1 equals 0, which means x is 1. So we have 3 solutions. We have a set of repeated solutions, but x equals -1, -1, and a 1. So we have that multiplicity of 2, but notice how even with that multiplicity, if we write it all out, we still have 3 solutions. In this case, they're all real. So let's take a look at one last example here to figure out how we can find the number of solutions. Now, I'm going to factor this one by grouping. We've got x cubed times x plus 1 plus 8 times x plus 1. And then we end up getting our x plus 1 times x cubed plus 8. Now this x plus 1 is factored as much as it can. This x cubed plus 8 is actually a perfect square, or is actually a sum of cubes. And so what we want to do is break it down. So we still have our x plus 1. To find solutions, we want it equal to 0. And we're actually going to have an x plus 2 times x squared minus 2x plus 4. Okay, now that that's broken down, this can't be factored, this can't be factored. This is still a square. We need to factor it, but it's not going to factor beautifully. So we actually have to go back to our quadratic formula here to factor it. So 2 plus or minus the square root of -2 squared minus 4 times 1 times 4 all over 2 times 1. X equals 2 plus or minus the square root of 4 minus 16 over 2. So x equals 2 plus or minus the square root of -12 over 2. Now 12 can factor down to 6, 2, and 3. So we can actually factor a 2 out of it. And because it's negative, we can factor out that -1, which breaks down into I and I. So we can factor a 2i out. So this becomes 2 plus or minus 2i root 3 over 2. Well, these 2's all simplify. And so really our other option for x is 1 plus I root 3 and 1 minus I root 3. So what are our 3 solutions here? We have, or our 4 solutions here that we have. We ended up with x equals -1 from this piece, x equals -2 from this piece, and then our last piece here actually gave us x equals 1 plus I root 3 and x equals 1 minus I root 3. And those are the 4 solutions. In this case, notice how we had 2 real and 2 imaginary. So using this, we can then figure out using that fundamental theorem of algebra, we can decide how many roots are we going to have to help us figure out how far do we need to keep factoring. Now, we always want to get it down into x plus something or x minus something or x equals something, but using that fundamental theorem of algebra, I know I should only get 4 solutions here. What are those? Some of them will be real, some of them will be an imaginary. We can use the graph, just like we did earlier, to decide how many reals and how many imaginaries we're going to need. And then based on that, we can figure out what we got. If you have any questions, feel free to reach out. But that is how you can use the fundamental theorem of algebra to help us find all of the possible solutions.